Okay, Physics Chapter 15. Turn to your book to page 488 and get out your Chapter 15 notes. And we'll go through these bullets one at a time. So a battery example. So in this space, I want you to draw this. So if we were to have, let's just say like a D cell or a C cell battery. Would have a positive side and then the negative side on this side, and let's say we were to somehow connect a wire and hook that up to a light bulb. All right. And in the light bulb is a filament. So the electrons are going to travel, although we don't show it this way in our circuitry, they're going to travel from the negative side to the positive side because electrons have a negative charge. They're attracted to the positive charge. And as they go through this light bulb filament, they're going to generate heat through that piece of metal. Okay, they're going to do useful work and cause that filament to glow, and that will generate light. So that is just a very simple battery circuit that we've drawn there. So our first bullet is about voltage. Okay, we study voltage in chapter 14 a great deal, and what I want you to think of as voltage in this chapter, just think of it as electrical pressure. So it influences how much work that can be done, all right? And we've got another term called current. I'll give you the mathematical definition of this in a minute, but current is how many electrons per second. So both of those influence how much work can be done by these electrons. Think of a circuit. In a circuit, voltage is if the current is water in a hose, and voltage is the water pressure. Both of those things influence how much work can be done. All right. The more water you have, okay, so that'd be kind of like current. The more, if you're washing your car, the more dirt you could get off. And the more pressure behind that water, the more dirt you could get off. So the more work you can do. So both of those things influence the amount of useful work. All right, so the current equation, and we don't use this in this chapter in any of our calculations, okay? Current is, we use the letter I for current, okay? V for voltage, I for current. And I is going to be the change in the charge over the change in time, okay? And the unit for that, charge would be coulombs, and time would be seconds. So coulomb per second, we call that an amp. And we'll use the letter A to represent amp. All right, so I'm going to erase all this if you need to pause it for just a second. Okay, a simple circuit. So let's draw that. All right, you've got some space to draw this. So what you do for a battery, you draw a long line and a short line. And all of this represents the wire. And the long line on a battery represents the positive side, and the short line, the negative side. The way in electric circuitry that you show the flow of current is from the positive side to the negative side. This actually isn't true. We know that, but when electricity was first being studied, that was the thought. Okay, so we show it going from positive to negative. Of course, this would be our voltage source, such as a battery. All right, from now on, you don't have to draw the plus and the minus. A long line means positive, a short line means negative. But for this first one, I wanted to draw that. So that should go under the simple circuit bullet. So let's look at, now, the way this is drawn from positive to negative. We know electrons actually go from negative to positive. But it's shown positive to negative because that's the way it was thought of for such a long time. And all of the electrical drawings show it that way. So instead of changing that, we just give this a new name, conventional current. Okay, so it's shown positive to negative. All right, let's look at 15.1, and this is on page 490. So 15.1 says, draw the current in the following circuit. All right, so let's just draw a simple circuit there. So the way that we show the current is going out of the positive side of the battery and into the negative side, and we'll just draw a little I there for the current. All right, if you'll turn your notes to the top of page 2, let's look at the concept of resistance. Okay, resistance is impeding the flow of charge. Okay, so a resistor is also where useful work can occur. So I'm going to go ahead and pause the video if you need to. I'm going to erase. Okay, and the first thing that we want to write out is Ohm's law. So Ohm is a scientist, and that is V is equal to IR. So you have to memorize this equation. V is voltage, so the unit would be volts. I is current, so the unit is amps. R is resistance. Resistance, the unit is ohms. And the symbol for ohms is the Greek omega. So you'll be using this equation a lot. So let's draw underneath that a simple circuit with a resistor. The way you show a resistor in a circuit is this squiggly line like that. Okay, so the current's going to flow out of the positive side through the resistor and into the negative side. So that's how we designate a resistor. That is where useful work occurs. So that resistor could be a light bulb. It could be a heater. Sometimes in circuits you have resistors just to smooth out voltages, so it might be a case where you're not actually doing something that might be useful to a human, but it's useful to the electronic device in order to smooth out voltages. So let's look at On Your Own 15.2. Flip over to page 494. Okay, and that says, I'm going to draw that circuit real quick here. So, got a battery at the bottom, resistor at the top. positive side of the battery is on the right, 15.3 volts. And it says in our circuit that our current is equal to 0.023 amps. So the question states, draw the current flow and determine the resistance. Okay, the current flow coming out of the positive side of the battery, going back into the negative, right? That's supposed to be an arrowhead there. Right, so if we know that if V is equal to IR, we want to know the resistance R is equal to V over I. Voltage is 15.3 volts. Current 0.023 amps. So that is 665.2, and the unit is ohms. So there you go. The math is not too bad, is it? All right, I'll let you pause that if you're still writing, and I will erase. Okay, let's keep V equals IR handy. And the next concept we're going to look at is electric power. Electric power. So in your notes it says power is energy per unit time. We also studied power in chapter 8, I believe. And there's 3 equations, and they all really come from each other. They're derived from each other, but you need to memorize all 3. Power is equal to current times voltage, so that's one of them. Power is equal to current squared times resistance. All of this is just rewriting V equals IR. So you need to know that one. And then the third way, and this is the way that you'll probably use the most by the time the end of the chapter occurs, is power is equal to V squared, voltage squared, over resistance. The unit for power you have seen before. It is watts. All right, let's look at on your own 15.3. So you are turning to page 496. So we should be able to get both of these on this board before I have to erase. Okay, it says a heater is rated to draw 13 amps and has a resistance of 9.3 ohms. Assuming 100% efficiency, how many watts of power does it produce? All right, so we're given the current, I. We're given the resistance, R. So power, we'd probably want to use this second equation. Okay, power is equal to I squared R. So that will be 13 amps. Resistance 9.3 ohms. Okay, and that is 1,572 watts. Let's look at 15.4 right underneath 15.3. It says an electric motor runs on a 1.5 volt battery, draws 0.32 amps of current. How much power does it use? Okay, we know the voltage, we know the amperage or the current. So power, we'll just use IV. So that's 0.32 amps times 1.5 volts. Right? And that is 0.48 watts. Okay, so that is the second page of notes. All right, if you need to pause the video, go ahead, and I'm going to erase. All right, we're on page 3. Switches and circuits. Now, in the classroom, I demonstrate this, but you've got some space to draw a circuit that has a switch in it. Okay, so we've got a voltage source, a wire, and that represents an open switch. Okay, so if you open the switch, so in this, the way we think about it, we would turn the switch off, but that opens the circuit. It disconnects the wiring, all right? Current can't flow. Okay, so this is just an open circuit. Electrons won't flow due to an incomplete connection. In fact, they don't even leave the battery, all right? They don't congregate up here at the switch. The current will never leave the battery if the switch is open. Okay, the next concept is series versus parallel circuits. So a series circuit, all devices must have connection for current to flow.